Yes, sir. Can you say that one more time, a little bit louder? Oh, I'll show. I got yours. I just got it yesterday. I will put that in. Yes, sir. Right. Coy, can you shut the door behind you, please? Thank you. All right. How's everybody doing today? My day's been on like 10 all day long so far. Been full speed ahead. It's crazy. Had my first glass break today. Not good. That's all right. I don't mind glass breaking. I had a student forget to wear shoes. So if you forget to wear shoes, I give you shoes. I have like 3 pairs, right? And I asked the kid, what's your shoe size? And he said 15.5. And I'm like, I don't think I got any of those. So it was good. It was good. He just had a seat for the day. Like 15.5. That's giant feet. All right, let's take attendance here real quick.
Oh, I see it.
Landon.
Here.
Thomas.
Here.
Coy's here. Michael. Andrew.
Here.
Keegan.
Here.
Owen.
Here.
Dylan.
Here.
Josh.
Here.
Nathan.
Here.
Nick. Caden.
Here.
Taylor. Aiden. Jake. Matthew. Oh, Matthew did it. And Brady. Sweet. All right. So you found my cow, did you? All right. How you doing today, Cole?
I'm doing okay. Thank you for asking.
Hey, we'll see you tomorrow, right?
Yeah, today's the last day.
Super pumped. Anybody solve my riddle for the day? Not really a riddle.
Yeah, I already have some more. Happy Halloween. No? I mean, you could say like a million different things. You could just say Happy Halloween. Yeah, I mean, it could be like, I can get this. This is like a joke, so it's not like a riddle.
Yeah, it's a little interesting, but let's put it up.
See you next.
I'm going to eat you. That's what he said.
Okay.
The web was the trick, and you are the treat.
How are we supposed to never know? How are we? That does not count for a riddle.
Web is the trick, and you are the treat.
That's not even a riddle.
I
like it though.
How tasty are flowers?
Guys, we're still undefeated.
Still undefeated. All right. So today we got a few things we're gonna. I want to get through real quick, so that tomorrow we can do our lab. Tomorrow we're going to be calculating gravity. Gravity, actually. Do you guys know what gravity is?
What is gravity?
The number?
Earth hugging.
Oh,
9.8.2.
There's 2 points.
9. A lot of people say 9.81. Is that true? Is it meters per second squared?
Like government or
Yes. Yes. It's actually not 9.81 meters per second squared. That's what everybody tells you. It's actually negative 9.81 meters per second squared.
That's what you said.
It drops. We're going down, right? There is no down. Is there a down? There's down. All right. So we're gonna do. We're gonna get to our notes a little bit, and then we're gonna hit our Fab Five. Have you guys heard the Fab Five in physics? We're gonna hit the Fab Five here real quick. It's 5 equations. Tomorrow we're gonna look at one of them to calculate the acceleration of gravity. All right. So you might want to. Did we finish with? You guys created the story, and then you had someone else graph it.
Yeah.
Did you guys get that far?
Yeah.
That's what I'm talking about. All right, so let's see if I can present this real fast. Cole, you're coming on the right day. Tomorrow we got a lab day.
Yay. Dude, I'm tired. Like, I can't give you enthusiasm.
Oh, are you excited to not sleep in tomorrow?
Dude, I don't even sleep in normally. Like, I've been getting up at the same time, so.
Okay. We should be. Oh. I know. All right, let's see. We got to our two different. We're cooking. We already got through that. That was my one story. That was my other story. You did that. All right. We should be on example 17. Is that correct? Oh, sweet. We're super close to the Fab Five. All right. So if I look at this, this is a good acceleration problem. Okay. Jim walked 10 meters to the school, down the school hallway from the cafeteria to the band room. Cindy, who has an interest, got an interest in Jim. Did you see that coming or did you not?
I thought that she was gonna go for Harry.
Oh, yeah, Cindy and Jim, yeah.
Cindy, why is it because she has an interest in him records his position every 2 seconds?
Why would you not?
That's how
Yeah,
you do it. That's the stalker. You guys never taken.
I mean, hey, I'm not judging. I'm just kidding. All right, so Cindy developed an interest in Jim and records his position every 2 seconds. And note that he moves 2.6 meters every 2 seconds. All right. Let's see. At what time was Jim in the following positions? 3 meters from the cafeteria. All right. So he's walking down the hallway from the cafeteria. So I'm going to draw it out from the cafeteria. And he's traveling to, let me zoom in a little bit. He's traveling to the band room. That's pretty cool if they were 10 meters apart. Okay. 10 meters apart. Okay. And he's moving 2.6 meters for every 2 seconds. So that's all the information we know. All right. So what was the time when he was 3 meters from the cafeteria? So he traveled a total of 3 meters. Okay. Well, all you got to do is a little dimensional analysis. Okay. So 3 meters. You can't read that really. Let me change to a pen. 3 meters. All right. And he's traveling 2 seconds for every 2.6 meters. All right. So I got the answer to be about 2.3 seconds. However, if you have sig figs, it's about 2 seconds. All right. Same thing with the 7. All right. Same thing with the 7. Or 3 meters from the band room. If you're 3 meters from the band room, that means you traveled 7, right? All right. So do the same conversion. 7 meters. For every 2 seconds, you travel 2.6 meters. For the second one, I got 5 seconds. Just kind of makes sense. Oh, I did 7 meters, did my conversion 2 seconds for every 2.6 meters, and you get 5.38 seconds, but sig figs takes me to 5 seconds. Any questions on that? No? All right, and then graph it. Okay. Graph his position. Okay. So what I'm doing, he traveled a total of 10 meters. And if he's traveling at this speed, I wanted to see how much time it took him. So it took him a total of 7.7 seconds. So I'm going to find about 7.7 seconds in 10 meters and just draw a straight line. That's about the best I can do. Hopefully your line looks something like that. Or like that. Oh, Jim got a hot dog. Cindy sees Jim buy a hot dog at the cafeteria. And wrote it down. Definitely wrote it down. All right. So everybody's graph look like that? All right. Sweet. 2 definitions. We should know both of these. All right. We did a couple experiments that discussed this. All right. Make it a little bit larger for you guys. All right. The speed at any given time. All right. Instantaneous. All right. So most common is when you're driving. Driving a car, you look at your speedometer. That's how fast you're going at that specific time. All right. Most common. The average is the total displacement. And then we're going to hit the Fab 5. Moving on to acceleration. Sweet. Everybody good? All right. Here comes the acceleration. These are the Fab 5 equations we will be using. Now, do you have to write this down? No. You do not have to write this down. All right. What I would suggest you writing down, actually, what I'll do, actually pass this out. This is the lab sheet, or not lab sheet, formula sheet. You'll get to use all year long. Every test. This is a formula sheet that was given on the AP exam last year. One I'm using. All right. My pretty green has every single equation that you could possibly think of. Actually, not really, but that's a decent amount. Decent amount. There you go. All right, so if you look on the AP Physics 1 equations, have that on top, you will see the top 3 equations on the left. The top 3 equations on the left. All right. That is this equation. It's going to be this equation. And this equation. Those 3 equations are already on there. Okay. Now, essentially, we already know this. All right. You might want to write that one down. That's a good one to write down, actually. The very top one. All right. Acceleration is the change in velocity over the change in time. That's a good one to write down. All right. Yep. It's not too bad. And this one, if you want to write that one down, that's actually pretty short. You can do the change in velocity equals AT. The change in velocity equals AT. It's basically this just rearranged, right? If you multiply T on both sides, you get A times T equals the change in velocity. Same thing, just rearranged. Okay? We will actually, in tomorrow's lab, we will be analyzing this equation. All right, we'll be looking at that one specifically to calculate gravity. Okay? So those are the 5 equations, all right? As you notice, x is displacement now, okay? We're going to be using x to represent displacement. The rest pretty much makes sense. A, acceleration, v, velocity, t, time. All right. Everybody good? Guys are quiet on me today. All right, so just a concept question real quick. Concept question. A horse gallops with a constant acceleration, so they're constantly accelerating, of 3 meters per second squared. Which statement is true? Let's see. A horse's velocity does not change. The horse moves 3 meters every second. The horse's velocity increases 3 meters every second, where the horse's velocity increases 3 meters per second every second.
D.
It is D. Very good. All right. Acceleration is meters per second squared, or meters per second. So it increases 3 meters per second. There you go. Very good. Does that kind of make sense? All right. Hopefully you guys have heard that before. Not too bad. All right. Cindy's growing up. She's getting old. About to get her permit and starts to shop around and look for cars. Right?
It's a lot more efficient way to stop a gym.
Say what? Oh yeah, if you're driving a car, heck yeah. The salesman lets her know that the Audi R8 that she is looking can go 0 to 60 in 3.3 seconds. Would you drive an Audi 8?
Who gets an Audi R8 for their first car?
Hey, Cindy. Right? Okay. What is their acceleration in miles per hour per second? Miles per hour per second. All right. So I'm going to show you how to do this one real quick. Let's get back here. We already got the formulas. We're already on the back. Sweet. All right. So we are right there. All right. So the acceleration is the change in velocity over the change in time. Okay. So the change in velocity, final minus initial. Well, I go from 60 miles per hour to my final, minus my initial is 0. I'm stopped. Right? And then my change in time is 3.3 seconds. Okay? So I have my miles per hour per second. So you just divide those two. 60 minus 0 divided by 3.3. I got about 18, but if you round, you should get about, well, 1 sig fig. That'll be 20 miles per hour per second. So that kind of makes sense. You just divide them. So that's the acceleration equation. All right. And what is the acceleration in meters per second per second? Ooh. All right. So you have 60 miles per hour. What I want you to do first is convert that into meters per second. Do you guys remember the miles to meters conversion? 1609. All right, 1609 meters. It's 1 mile. 1 hour. Do you guys remember how many seconds? 3,600. Very good. So if you perform that calculation, I think that'll be 26.8 meters per second, but I still have to divide it by my original 3.3 seconds. Okay, have to divide it by my original 3.3 seconds in the story. And I got about 8.1 meters per second. Boom. Nailed it. Not too bad. I know we're just introducing to acceleration, but hopefully it's starting to seem all right. It's not too bad. Not too bad. Okay. Next, you don't have to write anything down, just some scenarios. Oh, wait. Oh, I got something better. Her mom lets her know that she can have the 1995 family Toyota Corolla. That's what she's driving. No Audi R8. Nice. All right. Concept question time. I'm going to zoom this up. All right. Now, in which scenarios does the car speed increase and which ones decrease? Okay. In which scenarios do they increase and which do they decrease? Anybody have a guess? Which one would be increasing? Yes.
Increasing A and B.
A and what?
A and D.
A and D. Why did you say that?
Because the acceleration from velocity.
You're exactly correct. That was a great explanation. So you are increasing speed because the acceleration and velocity are going the same way. If they're going opposite ways, my velocity is going this way, but I'm decelerating, so I'm slowing down. Right? All right. So B and C are the decrease. All right. Question B. In which scenario does the car have a negative acceleration? Oh, this is a tricky one, but you got this. Yeah.
B and D.
Which ones?
B and D.
B and D. Why did you say those two?
Because they're moving on less than X.
You're exactly correct. All right. B and D, because my acceleration is going to the left. Right? Anything left, down, west, all negative. Right? Beautiful. Not too shabby. Feeling all right? All right. We're going to apply I want you to try this one out. Try it out. It's a little tricky. If you need to ask a partner, ask someone next to you. All right? We're going to figure this one out. If you guys want to draw a picture, love drawing pictures. A picture would be great. All right? I'm going to draw a little picture in my notes. There's my flag. Sweet. Two more slides and we're done. Is there any questions so far? Anybody need a good jump start?
Pardon the interruption. Daniela Reiser to the front receptionist desk, please.
There you go. Yep. Very good. Sir?
Send you a breaking the law.
What?
Why are you jumping ahead as a professional driver? Yeah.
Yep.
It's over 20 months. Again, it's not over 20.
How do you know?
I'm guessing. But Cindy is most likely breaking the law.
That's true. That's true. All right. I'm going to go over this problem, show you what I did real quick. I'm going to make this large. All right. So this is how I worked out each. Actually, that's the wrong problem. This is how I worked out each problem. I drew a picture. I love, love, love drawing pictures. So of New Jersey, she says she's traveling to New York. As the ferry approaches New York, traveling in the positive x direction. That is huge. So it's positive in displacement, right? So my acceleration equation is delta v over delta t. So I did 0 minus 7.4, all right, over 12, my 12 seconds, okay? I got a negative 0.62 meters per second squared. However, going in the reverse direction, you have a negative velocity, okay? So I had 0 minus a negative 7.3, which makes that positive, and then divided by 13. Does that kind of make sense? How'd you guys do? Not too bad? Yeah, question.
Is there a reason why you only did 12 seconds and 13 seconds instead of taking it out to the next decimal place? Because the first one it's 12.3 seconds.
Oh, I just rounded. I did quick. I think I did. Did I get? Should still be right. Oh, all right. Not too bad. Now, on the next page, I have 5 steps to solving physics problems. 5 steps. Now, do you have to use these 5 steps? No, you don't. However, some problems seem, like the last problem on my quiz, seems so complex. But when you follow some simple steps, oh, I forgot about the bottom. As the ferry comes back, the sun sets, creating one of the most beautiful scenes. Oh, Cindy and Jim. All right. These are the 5 steps. Now, you don't have to write this down if you don't want to. But it is, I find it super helpful, right? To draw a picture. Drawing a picture, I'm a visual person. If I see a picture, I know what to do. Draw a picture. List my unknowns and knowns. That, if you're not a good drawer, that is key right there. List the unknowns and what you know. Super, super helpful if you do those 2 steps. Select the equation. So once you see what you have, what you don't have, you can create or pick one of the Fab 5. Right? You can pick one of the Fab 5, and that will help you solve it. Solve the equation. All right, these 2. Number 4. I do it sometimes, but I don't do it other times. Solve it symbolically. So just use the letters in the equation. I like to use numbers. I'm more of a numbers person. And then number 5 sounds super silly. Sounds super silly. Check your answer. Does this answer make sense? Now, when you're making like a sig fig, let's say you're at 2201, and you're like, ooh, I have to get to 1 sig fig. I'm going to get rid of all those. I'm just going to leave it there. That's my 1 sig fig. Well, 2 is not close to 2200. So I have to have my zeros, right? So stuff like that. Just check your answer. Super, super huge. Right? 5 steps, yeah.
What did you mean by symbolically solve the equation?
Let me show you. Let's do. Okay, like this. Let's say I had to solve for my initial. No, we're gonna make it easy. We're gonna go down to t. Let's say I had to solve for my velocity, initial velocity. Instead of plugging in numbers, rearrange the equation first. So I would have to multiply by delta t on both sides, right? So I would get a times delta t. So I would get rid of that. Equals that. Well, I have this on that side. So I have to subtract this over, right? Or, oh my gosh, subtract VF, subtract VF, right? But I still have a negative, so you're going to multiply by -1. So now you have your equation set up for initial velocity equals that, and then you plug in your numbers. So let's say my acceleration was -9.8. Say your change in time was 3 seconds, and your initial or your final velocity ended up being 0. So you can plug in your numbers at the end. I like to plug my numbers in at the beginning sometimes, but sometimes that makes sense to me as well. Does that kind of make sense? Yeah. So symbolically is just rearranging the equations, basically. One last problem, then we're good for the day. Okay. I want you to try this one out. Last one. Cindy got her provisional driver's license and driving with Jim, cruising at 20 meters per second. After a while, Cindy decides to show off, steps on the accelerator. So step 1, I'm going to draw my car. Nah, she's driving a Corolla. Sweet. All right. Cindy Bobby cruising down the road. She's cruising. 20 meters per second. So initial velocity. How fast are they moving after 5 seconds? Okay, that is how I would set it up. You guys have the question in front of you. I'm gonna bring it over here. All right. Hopefully you can see that right there. All right. So I drew my picture, traveling down the road 20 meters per second. I wrote my unknowns, right? You see over the computer. I wrote my unknowns. All right. I knew my initial velocity was 20 meters per second. Knew my acceleration was 2.4. Time was 5. The question says, what's my final speed? What's my final velocity? Okay. What equation are we going to use here? You guys pick one out that has the velocity final, velocity initial, acceleration, and time. Which one did I use? Velocity final, velocity. That's the equation I'm going to be using. All right. It's the very first equation on your equation sheet. Okay.
Daniela Reiser to the front receptionist desk, please.
All right. Now, all you have to do is plug in your numbers. Well, my velocity final, don't know it, but I do know my initial velocity was 20. My acceleration was 2.4. And my time was 5 seconds. And you just got to calculate. Does that kind of make sense how the 5 steps make it a little easier, right, to solve? And I got 32 meters per second. 32 meters per second. Okay. Now, how far did they travel? Okay. How far did they travel? Well, which equation do you? Let me write out my information. All right. So basically, I know my final velocity now. 32 meters per second. I know my time, but now I need to know how far they traveled. Same problem. Which equation am I going to use? Most likely my x equation. Right? Okay. So I got x is equal to my initial spot. Okay. Plus velocity initial times t plus half the acceleration t squared. Okay. Okay. So my initial spot was just going to be 0. So I can really just get rid of initial displacement since I'm calculating how far they just traveled. All right. So I got rid of that. My initial velocity, 20. My time, 5. Plus half the acceleration, which in this case was 2.4, times the time squared. 5 squared is 25. That's going to equal your x. Starting to get acceleration a little bit using the equations. All right. And your x. I got 2.6 2 sig figs. And 30. Yep. Okay. Any questions on that you guys can see? That's all I'm doing today. Tomorrow, we will be applying these equations. Well, mainly one of them. We're going to see if gravity is negative 9.81 meters per second. Is it?
But you're gonna say it's gravity real.
Is it real?
Measuring it with time.
It is a theory. The theory of gravity, right? Now, question. When I drop this marker, is the marker falling towards the earth or is the earth falling towards the marker? A little bit of both. The earth is actually coming closer. It's being pulled by the marker, but the marker is actually being pulled down more. So it. All right. We'll be analyzing that. I have a pretty sweet video. They create a silo and they create a vacuum out of the silo. Pretty awesome video. So anyway, we got about a minute left. Is there any questions on acceleration so far? We're gonna be doing 2 labs at the end of this week. One tomorrow, one probably Friday. Thursday or Friday. So we're gonna do some back to back. Hope you guys have an awesome day. You guys are awesome.
No idea.
Is this it?
I got it right on.
Cool, you like the shortcut? Pretty nice, huh? Yep. Is this making a little bit of sense? Yeah.
I didn't really get the first equations.
You didn't get the Fab Five? Did you get the equation sheet?
Yeah, I did.
Oh, then you're good. You're good. All right, let's see. How you guys doing? Were you able to follow most of that?
Yeah.